Okay, let's talk about something that sounds completely impossible. I'm talking about the ability to walk through walls. Not magic, but something even weirder, something that happens on a scale we can actually measure. This is the story of the great quantum escape.
I know, it sounds like something straight out of sci-fi. We're always told that quantum mechanics, all those weird rules, that's for the super, super tiny stuff, right? Atoms, electrons. But what if? What if something big enough for us to see could just pop right through a solid barrier? So here's the setup. It's 1985. A team of scientists is cooling this system down, and I mean way down, colder than you can even imagine, almost as cold as it's possible to get. And they ran into this total mystery. See, as things get colder, they're supposed to get calmer, more stable, but the rate at which their little system was escaping its trap, it just stopped slowing down. It hit a wall. No matter how much colder they made it, it kept escaping at the exact same rate. Something else was clearly going on.
And look, this wasn't some tiny little error in their measurements. This was a huge, glaring puzzle. It really blurred the line between the world we live in and that bizarre, invisible quantum world. So to really get what's happening, we're going to go right to the source. We're diving into a landmark paper from 1985, published by a team of absolute legends, Michel Devoret, John Martinis, and John Clarke. These guys designed this beautiful, elegant experiment to figure out what in the world was going on in that deep freeze. Now, the actual physics here can get pretty gnarly, but don't worry. The core idea behind it is something we can all visualize. Let's just think of it as the particle in a well.
So what were they actually looking at? It's called a Josephson junction. It sounds super technical, I know, but all you need to know is that this tiny little electronic circuit, under the right conditions, acts like a single big, a macroscopic particle. It was the perfect guinea pig, big enough to build, but small enough to still play by quantum rules.
Okay, let's make it even simpler. Let's just forget the circuit entirely for a minute. Imagine a marble. It's sitting at the bottom of a shallow bowl or a valley. It's trapped, right? In physics speak, that's our particle in a potential well. The marble is our big particle, and the valley is the energy trap it's stuck in. And the whole point is, how does it get out? Well, it turns out there are really only two ways for our marble to make a break for it. The first way is the normal, classical way we all get. It's called thermal activation. Basically, you add energy, heat, and the marble starts to jiggle around more and more until, it gets enough of a kick to roll right up and over the side of the valley. Easy. But then, there's the quantum way, quantum tunneling. Here, the marble doesn't go over the wall, it goes through it. It just appears on the other side, like the wall wasn't even there. And that seemingly impossible escape is exactly what this whole experiment was designed to catch in the act. How do you even prove something tunneled through a wall instead of just climbing over it?
Well, the whole genius of the experiment comes down to this one simple question. What if we take away all the heat? What if we get it so cold that our little marble has zero energy to climb that hill? If it still manages to get out, well, then there's only one way it could have happened.
So this gives us two totally different predictions. You've got team classical physics with thermal escape. That needs heat. So as you drop the temperature, the escape rate should drop right along with it, all the way to zero. But then you have team quantum physics with quantum tunneling. Theory says this doesn't care about temperature at all. It's a purely quantum thing. Even at absolute zero, the particles should keep on tunneling out at a steady rate.
I mean, the setup for this thing was just a work of art. They took their Josephson junction and stuck it inside what's called a dilution refrigerator, a machine that can get things unbelievably cold. We're talking just a few thousandths of a degree above absolute zero. And then they just watched. They measured the escape rate again and again and again as they nudged the temperature lower and lower.
Okay, this is it, the moment of truth. The experiment is running. It's colder than anywhere in the universe. What is the data going to show? Is the particle's escape going to freeze solid, or is it going to do the impossible and tunnel right through that barrier? So let's just recap what everyone expected to happen, based on normal, everyday physics. As the fridge gets colder, the escapes should get more and more rare, basically heading straight for zero. Simple as that. Yeah, that's not what they saw. Not even close. What their data showed was, it was astonishing. It was the very first piece of solid proof that these bizarre quantum rules could apply to something big enough to build in a lab.
So check this out. At the warmer temperatures, and I'm using that term loosely, we're talking about 100 millikelvin, the escape rate was pretty high. They cooled it down to 50, and the rate dropped by about half. So far, so good, exactly as predicted. But then, as they went even colder, the rate just flattened out. It hit a plateau.
And the paper is super specific here. It says that below about 25 millikelvin, the escape rate just stopped caring about the temperature. It became totally constant. The particle had zero thermal energy to get over the barrier, and yet it was still escaping at a constant measurable rate. That, my friends, is the unmistakable fingerprint of a temperature-independent process.
So the team took that constant escape rate and translated it into something they called an escape temperature. It's just a way of measuring the energy of this purely quantum effect. And the number they measured, right there in the quantum zone, was 37.4 millikelvin.
Okay, now get ready for this because this is the part that gives me goosebumps. For decades, quantum theory had already predicted what that number should be, if quantum tunneling was real for a macroscopic object. The number from the theory books was 36.0 millikelvin.
I mean, look at those numbers. They are insanely close. In their paper, the scientists used very careful academic language, saying it was in excellent agreement with the prediction. But let's call it what it is. It was a perfect match.
And this is the smoking gun. This is why this experiment is legendary. They didn't fudge any numbers, they didn't tweak anything to make it fit. The paper is super clear. They did this with no adjustable parameters. They measured all the properties of their circuit, plugged them into the theory, and the number that came out of the equation was the exact same number they were measuring in the lab. That's as pure as the test of a theory gets.
So, okay, it's an amazing result. But so what? What did it really change? Why does this one experiment, this one quantum leap, matter so much, even today?
Well, this was huge for a bunch of reasons. First, it proved that the spooky rules of quantum mechanics weren't just for tiny little atoms. They worked for bigger things, things you could actually build and control. It took this bizarre prediction right out of a textbook and showed it was physically real. It also showed us something profound, that even at absolute zero, the universe is never truly still. There's always this underlying hum of quantum activity. And maybe most importantly for us now, this very principle is a cornerstone for building the qubits that power modern quantum computers.
What Devoret, Martinis, and Clarke did was they opened a door. They proved that sometimes the impossible is just quantum mechanics, waiting for us to design an experiment clever enough to see it. And it kind of leaves you wondering, doesn't it? What other impossible quantum leaps are hiding out there, just waiting for us to find them?